Hey guys, this is Gavin, and this is Lecture 4 titled ESP32 Programming Part 2. Before we get into today's content, however, we're going to go over Project 3 real quick. So, the official due date for Project 3 is Friday, week 9 at 11:59 p.m. This is kind of the recommended due date as a reminder so that you guys can keep on pace with our program. So, make sure you ask questions and seek help, whether it's online on Discord or lab hours with instructors so that you can finish it on time. And hopefully, you've learned some of these concepts, which are embedded systems, microcontrollers, getting your hands on the ESP32 for the first time, as well as programming in Arduino IDE and pulse width modulation, which is PWM. And this is going to be important for fall quarter, which we have new deadlines. So for the full $20 refund for fall quarter, the final project deadlines are going to be for projects 1 and 2 by the end of finals week, which is going to be December 13th at 11:59 p.m. And then for projects 3 and 4, they're going to actually be due by the end of winter break. So this is January 5th at 11:59 p.m. And this is going to be the Sunday before the Monday of winter quarter when instructions start. So make sure you ask project specific questions in the ops help channel during the time of winter break. You guys will have time to work on projects 3 and 4. So I definitely recommend bringing home your kits with you to work on it. And we're going to try to answer ASAP during the break on the ops help channel. So moving on to project 4 now. In project 4, you're going to build a sundial that measures the brightness of your room by controlling a micro servo with an ESP32 and also a photoresistor. Hopefully, you're going to learn by the end of project 4, getting more comfortable with ESP32, servos, as well as Arduino libraries, and tips for programming in Arduino IDE, and also tips for project 4. And with that out of the way, we're going to get into servos. So a servo motor is a type of motor that converts electrical energy into mechanical energy to achieve precise control between 0 degrees and 180 degrees. Servos have three different wires, at least for ours. The power one, which is the red wire, ground, which is brown, and pulse width modulation, which is the orange wire. So you want to insert the male to male jumper wires in your ops kit into the female end of the micro servo, and then you want to connect the other end to the ESP32 on a breadboard. Um, so you'll be controlling the position of the servo with a photoresistor in Project 4, as well as a potentiometer in Checkpoint 1 to make a sundial. And for the servo pinout, you're going to connect the red power to the 5-volt pin of the ESP32, the orange wire, which is the PWM one, to the GPIO pin of the ESP32. You can do it for any of them, but for our project, we're going to be doing pin 10. And then you're going to connect ground, which is the brown wire, to essentially ground of the ESP32. So now we're going to get into Arduino libraries. So an Arduino library is a collection of pre-written code that makes it easier to interface with hardware or perform specific tasks. So these libraries are made by either Arduino's development team or just community members of Arduino. And these libraries can be downloaded from the libraries manager. It's that going to be that book icon that you see on like that left toolbar side. So the ESP32 library will need to be installed to control the servo in Project 4. So we're gonna run through how to do this. So you're gonna have to first click on the library manager icon, which is gonna be on that left toolbar side. It's got that book icon. Then in that search bar under library manager, type in ESP32 servo. That first result that you see by Kevin Harrington and John K. Bennett is the one that we're going to install for our projects. So make sure you download the correct one for project 4. So in order to use the servo library, you're going to use the hashtag include ESP32 servo.h. What this does is that it includes the library in your code. So in our example code, you can see that in our first line, we have done hashtag include ESP32 servo.h to include that library so that we can use it. Next, these next set of functions and initializing objects is going to be necessary so that you can control the servo. So servo, your servo name initializes a servo object to whatever you want to name the servo object. So in that space where it says your underscore servo underscore name, you can actually name your servo whatever you like. But make sure you use that servo name for the next functions that you're going to see below. So our first function is going to be your servo name dot attach and then int pin. So this is going to link the servo object to the physical pin, which is going to be int pin on the ESP32. And in our example, we have created a variable named int servo pin, and we have assigned that variable pin to the pin number of the servo's PWM pin, and we're going to use pin 10 of the ESP32. So in our example, we've used the name myServo, and the way we use this function was in void setup, which we did myServo.attach servo pin. And reason why we want to leave it in setup is because we only want to link the servo object to its physical pin like once. We only want to run this function once. Next, in void loop is where you actually write to your servo and actually specify to the servo what specified degree you want. And you can do this with your underscore servo underscore name dot write. And then inside is going to be int angle, which is going to be your argument. So you can actually move that between values of 0 and 180. So in our example code, we have myServo.write 0 as well as 90 and 180, and these are separated by 1 second delays. So if you would predict what this code would do, essentially what it would do is it would just move the servo from 0 degrees, wait for 1 second, move it to 90 degrees, wait for another second, and then move it to 180 degrees, and then just repeat that in a loop. So besides the servo in Project 4, there's going to be some couple other ESP32 concepts that you might want to be aware of. So first one is going to be PWM, which we've kind of revealed a bit in Project 3, but want to go over again. So on the ESP32, the board is only a digital source, which means that it can only output either a high or low voltage. This is going to be between 3.3 or just 0 volts. So how does analog write then output analog signals between 0 and 3.3? Like how does it do 1.65? The way it does this is through pulse width modulation, or PWM for short, which is an oscillating digital waveform that emulates an analog output. So let's say I want to emulate 1.65 volts. The waveform that I would do is I would have 3.3 volts for 50% of the time on, and then also 3.3 volts 50% of the time off. And this is going to average the value out. And by doing the average, the waveform is actually going to be 1.65, which is half of 3.3. So by oscillating a signal from high to low quickly, the average voltage over time will be between high and low, which is going to be an analog value. So the duty cycle of the PWM wave is the percentage of time where the signal is high. So for example, like I said, a 50% duty cycle is going to translate to an average value of 1.65 volts, which is 50% of 3.3 volts. And this is going to allow us to output a continuous range of voltages between high and low. And that duty cycle is going to be controlled by a timer, and that timer is inside actually the ESP32 microcontroller. So on the diagram on the right, you can see we can actually use values between 0 and 255. And you can see that some of these values that we put in have varying duty cycles. For example, 191 is going to have a 75% duty cycle because it's going to be on for more longer, just so that it can like get closer to like a higher value. Whereas analog write 64 It's not going to be as high value as 191. So you're going to see that have a 25% duty cycle. So ADC and analog read is our next concept that I wanted to go over again briefly. So analog read is that function that utilizes the analog to digital converter inside the microcontroller to measure real-world analog signals and convert it to a digital signal. So essentially, um, almost all signals in the world are like analog inputs. If you've taken Physics 7E, you might be aware, like, for example, light waves are like analog. Also, sound waves. So honestly, almost every signal in the world is in the real world is analog signal. And how do we convert this to digital? We use an analog to digital converter. So the measurement resolution of the ESP32 is going to be in 12 bits. And that's how we get the function to return values from 0 to 4095. Essentially, what that means is 2 to the power of 12 is 4096. So that's why we have the range between 0 and 4095. And then the last concept I want to go over is a resistor divider. So in project 3, um, you've had a resistor divider actually in the potentiometer. And in project 4, we're actually going to be using the potentiometer once again, and then also the photoresistor in a resistor divider. So this concept is going to be really important for project 4 as well. So a resistor divider is a circuit configuration with two resistors. And the reason why we put it in this configuration is we want to scale a voltage down to another voltage, V out, which is smaller. So the resistor divider creates a ratio of two resistors to achieve a desired output voltage. Um, and the values of R1 and R2 are connected in series, where V in is the input voltage and V out is the output voltage across R2. So the formula is going to be V out is equal to R2 over R1 plus R2, and that's going to be in the parentheses that you can see, times V in. So if you're going to take E70A or 70B, you might actually go over the derivation of that formula. We're not going to go over it today, but if you ever want to use a resistor divider for your projects, this is the formula that you would use. And yeah, like I said before, um, Project 4 is going to have multiple resistor dividers. So first one is going to be a potentiometer, which is an adjustable resistor divider, where a wiper or slider divides the resistive elements into two adjustable parts. The second one is going to be a photoresistor, which is in series with the 4.7K ohm resistor in your kits. And that's going to create a light dependent resistor divider. The reason why we want to do this is because the photoresistor's resistance is going to change with the intensity of the light. And we want to use this to sense the light levels for our sundial. And the resistor divider in project 4 is going to convert this change into a voltage that is going to be easily measured by the ESP32. I'm going to go over some final tips that I want to give you guys for project 4, as well as just an outlook into winter quarter and a recap of what we did during fall quarter. So, if you ever are confused of what a specific Arduino function does, or like you just want to learn more Arduino functions, you can always visit the Arduino language reference. This is going to have an explanation for most common Arduino functions that you guys are using. Make sure that you understand the purpose of each function of Arduino functions in a code, just so that you don't blindly copy and paste code and that you're actually learning, because that's the whole purpose of open project space, right? So another tip I wanted to provide you guys for project 4 is using the serial monitor. So in project 4's case, actually, it's going to be some tool that's actually necessary so that you can tune your photoresistor. So serial.print is an excellent tool so that you can use to help debug programs as well as tune sensors. And yeah, like I said, we're going to be tuning the photoresistor. So we're going to be printing values to track the photoresistor's value in a resistor divider. This is so that we can find the photoresistor's value when the room is the brightest and also when the room is the darkest, so that we can determine the range of the photoresistor, and that value, the minimum value and the maximum value, is going to be some number between 0 and 4095. So after you've tuned your photoresistor and found the values, the minimum value and the maximum value where the room is the brightest or when the room is the darkest, and by the way, this process, you're going to use the serial monitor to find these values. Um, Once you found this range, you're going to now remap the photoresistor range to the servo range, which is going to be from 0 to 180 degrees. So we're going to achieve this using the map function. And the map function is actually a built-in Arduino function that you can use straight off the bat without, downloading an external Arduino library. So the syntax for a map is going to be map and then in parentheses input value. That input value is going to be usually like the analog read value that you get from either, a potentiometer or a photoresistor, for example. And then the next values are going to be min range 1, max range 1, min range 2, and then max range 2. Min range 1 and max range 1 are going to be the minimum and maximum values of the first range. Um, in Project 4, for example, it's going to be the potentiometer or the photoresistors range. And then min range 2 and max range 2 are going to be the minimum and maximum values of the second range, which is going to be the servo between 0 and 180 degrees. So for the map function in Project 4 checkpoint 1, you're going to need to map the range of the potentiometer, which is between 0 and 4095, to the servo range of 0 to 180 degrees. So in our example code below, we have a integer variable named pot value, and that's going to be equal to analog read of the pot pin. We're going to be reading the analog signal at the pot pin, and that's going to give us a value between 0 and 4095. Next, we're going to have and use the map function. So the way we do this is map, and then in parentheses, we're going to have pot value in that first value there. And then second value will be 0, which is the minimum range of the first range. Then 4095, which is the max range of the first range. And then the next values are going to be, 0 and 180 because that's the range of the servo. So in short, that is how you would use the map function. And you can actually use the map function as well for the photoresistor, which you're going to use in the second checkpoint. And then lastly, I just wanted to go over what we've done in fall quarter and also winter quarter, which is actually quite a lot. So you guys should be proud of yourselves. So in fall quarter, we've completed 4 projects in total. The first project was Let There Be Light, and then 555 Piano, as well as the LED RGB Wizard project, and then your last project is going to be Sundial. And hopefully in fall quarter, you've learned Ohm's law, how to breadboard and solder circuits, basic circuit analysis like nodes, what nodes are, etc. And then programming with the ESP32, and then also programming in Arduino IDE. And then moving on to winter quarter, building upon what you guys have learned so far, which is already a lot, we're going to actually learn more in 4 new projects. So project 5 is going to be an iPodUino. That's going to be an MP3 player based off of an ESP32 microcontroller that's going to be able to skip tracks and play some tunes. And then you're also going to be able to add some of your own songs on a micro SD. Then project 6 is going to be a wireless weather station that's going to have 2 ESP32s, and one is going to be transmitting signals, weather signals of temperature and humidity, and then the other one is going to receive that on the other end and display that on an LCD display. And then project 7 is going to feature a digital stopwatch. You're going to learn about interrupts and timers in this project, as well as you're going to be able to program, your very own digital stopwatch. And then the last project in winter quarter is going to be a pretty exciting one, which is a capstone PCB design. It's going to be a remote control so that you can control your capstone rover in spring quarter. So the reason why we have it at the end of the quarter is that you're going to actually design it, and then you're going to have your design files sent to a manufacturer so that they can actually build your PCB, and you'll be able to get your PCB in spring quarter afterwards. So in winter quarter, we're going to be also learning a lot. We're going to go over a couple of communication protocols, UART, SPI, I2C. Those are very common and popular communication protocols that every engineer should know about. And then as well as interrupts and timers, and then also PCB design, which is also a very interesting topic. And so yeah, on behalf of the ops team, I want to thank you guys so much for an amazing fall quarter. You guys have learned like so much in very short amount of time. And in winter quarter, we're gonna have four new and exciting projects. So stick around for that. But other than that, have a great finals week. Good luck on your finals. Have a great winter break, and see you in winter quarter.